Hello everyone, welcome back again on our Big O playlist in computer science. So today we will again be solving one of the question in time and space complexity. Before we do that, as we always do, let's do a quick recap on what we have learned so far. If you would like to skip this part, then it's fine. But if you have already gone through previous parts and come across any queries, then feel free to drop the question or query in the comments part and I will try my best to answer it. So in terms of what we have learned so far, we started with our big O notation. What is its significance? Where it is used in computer science world. Then we talked about the algorithm, what an algorithm is, and then a few related terminologies on big O, big omega, and big theta. And then we learned that whenever we are determining the complexity, then we should always look out for a tightest bound on it, be it space or be it uh, time complexity. Then we talked about the best case, worst case, and expected case scenarios for a given algorithm. And we understood that it mostly depends on the type of data which we are getting. So basically, best case describes when we are able to run our algorithm very quickly for a given set of data. And then worst case is like our algorithm has to do a lot of hard work to determine something or to do something, whatever was the intention of writing an algorithm. And then expected case is average case on a typical general day, what uh, kind of data we have based on that. And then we learned about one of the most powerful concept in computer science, time and space complexity, wherein time complexity is about how much time my algorithm is going to take. So representing that time in terms of input, and then space is how much memory uh, my algorithm is going to take again in terms of input. Then we basically looked at some of the common patterns or steps you will always encounter in any type of algorithm you are writing. So basically, knowing these common patterns or common complexities can get you quickly see like how much is the complexity coming up for that particular step in a given algorithm. So we looked at some of the common complexities like order of 1, order of log n log n square 2 raised to the power n, and many more. And then we talked about amortized time. And the example we took is array list, which is a dynamic resizable array. Then we looked at log n complexity with an example of linear search and binary search. So in linear search is basically if we have given an array and we are also given a number to find that number in that array, then one approach is like linear search, wherein we are iterating through each element of the array and then finding it out whether the number is matching with the given number, right? So in linear search, the complexity or runtime or time complexity is order of n. Whereas now, if we want to optimize it and we use binary search, wherein the assumption was that my given array is sorted. So in that case, to find the given number, we just start at the mid position in that array. And then likewise, we just filter out one half and then we just look at the other half because my data is sorted. So in that respect, we are able to find a given number if it's there or not in log n time rather than n time. right? So for example, if we are given, let's say, if we are given for 16 elements in our array, then with the help of binary search, we will be able to do it in four steps, which is like uh, log log 16 is log 16 is actually 4, right? And then we talked about recursive code complexities with some examples. So recursive code is, or recursion is, basically when we call a method, same method again and again to solve a smaller problem, right? And then we looked at some of the common points which we can remember to when we are determining the time complexity or space complexity. We can always drop the constants, and likewise we can drop the non-dominant terms. So basically, first we in the previous parts in this playlist, we first covered all these concepts with some examples, and then we basically picked some questions. We went through determining their runtime complexities, and that is what we are doing today as well. We will be picking up one example or question and we will be solving its runtime. Okay, with that, let's keep started. So in this, the question is we have to find the runtime of this algorithm, right? So what we are doing here is, so we are given an array, right? And then uh, we have a for loop here, right? So in this for loop, what we are doing is we are first going through this, or whatever is the length of the array, but not till entire length, rather till half of that length, right? So it's I starts from 0, I is less than array length divided by 2, and I plus plus, right? So what it means is that if my array is something like 1, 2, 3, 4, 5, right? So let's say this is my array wherein I starts from 0, 1, 2, 3 till 4. So I am saying that my array length here is 5. So 5 by 2 is 2, right? So I is going to go from 0 till this value less than 2. So it means I will go till 0 and 1, till 1. So I will say including, right? So first I will be here, then I will go here, just 2 steps. Likewise, if I take another example, let's say my array is 1, 2, 3, 4, 5, and 6. So here the length is 6. So 6 by 2 is 3. So I will go from 0 till 2. So in the first scenario, I will go till here. In the second scenario, I will go till here. So it's just going half, right? And what we are doing inside it is we first have this statement. So this statement, what we are doing, so we are trying to find other, right? So other is array length minus I minus 1. So you can also think of it like this, that we are doing array length. So array length in this case is, first example is 5. So 5 array length minus 1, right? So we can write it array dot length minus 1 minus I. We can think of it like this as well, right? So array length minus 1 is always my last element in the given array, because array length in this case is First case is 5, right? So 5 minus 1, which is 4, right? So I am saying array length minus 1 is always the last one. Similarly, array length minus 1 in this case is going to be uh, 6 minus 1, which is 5. So this is 5, right? This is fifth index. So what I am doing is array length minus 1 from the end, go back I steps, right? So when, let's say, my array is the first one, which is 1, 2, 3, 4, 5. So in this case, 0, 1, 2, 3, 4. So so basically when I is 0, then other will be from the end 0 step back, right? So other will be 5. When I is 1, when I is reaching to 1, this index, then I am saying, okay, I has moved one step forward, so I will move one step backward. So I was at 5, I was at index 4, so now I will go to index 3, right? So this is correctly written. So it is going to be 4, then it is going to be 3. So this is kind of I is actually a forward pointer, we can say, or and other is actually the backward pointer. So because I is going in this direction and other is going in this direction, right? So once I do this, once I know what is my backward pointer location is, then this thing is simply swapping the values, right? So swapping the values means, uh, so in this, when I is 0, other is here, right? So what I am doing in the next three steps is I am just swapping these values. So 5 will come here, 2, 3, 4, and 1. So I have swapped the value with, at index I and other, right? When my loop will run again for I is equal to 1, so I will replace these two values. So it will go here and this value will go here. So it will be like 5, 4, 3, 2, 1. And we know that I will just go for 0 and 1 in the first example, in this example, right? So ultimately my array has changed from 1, 2, 3, 4, 5 to 5, 4, 3, 2, 1, right? So basically, now let's take one more example, this one. So we know that its length is 6, right? So now the first for loop, this for loop, it will run from 0 till its half. Okay, so 6 by 3, 6 by 2 is 3. So let me write down its indexing 0, 1, 2, 3, 4, 5. So in this case, I will go in this for loop from 0 till less than 3. So 0, 1, 2, right? So let me write it down. I is 0, I is 1, I is 2. So what will happen in this case? Other will be how much? So in this case, other will be at 5. Then when I is 1, so other will be one step backward, which is at 4. When I is 2, then other will be again one step backward from the previous one. So in this case, 3. So here I am increasing it and here I am decreasing it, right? Here I am increasing it, here I am decreasing it. So this is my forward pointer, this is my backward pointer. And what I am doing in each step I am doing a swapping, right? So in the first case, I will interchange the value or swap the values. So 6, 2, 3, 4, 5, 1. This is going to be my resulting array. Then when I am here, then next time when I is 1, so I will change its value from 6, 5, 3, 4, 2, 1. Now when I is 2, it means it's here. So other will be where? Other will be here, right? So I am again replace these values. So it will be 6, 5, 4, 3, 2, 1. So now if you compare it with my original array, so it was 1, 2, 3, 4, 5, 6. So ultimately it's reverse. So this program is for reverse. And in this program of reverse, how many times my for loop is running? It's running just half of the entire length of the given array, right? And then these steps are just in the constant time, all the 4 steps, right? So essentially my algorithm, this algorithm is running in term if my array length is n, or if I have n elements in this array, so this operation is I am doing n by 2 times, right? So that is what my complexity is, order of n by 2. So now order of n by 2 can be written as order of n, or maybe I will write order of n multiply by 1 by 2, right? So let me just erase it once because it's not very clear, and let me write it again. So my n by 2 can be written as order of n multiply by 1 by 2. So ultimately I can drop the constant and it is still order of n, right? So that is what my complexity is. So though in this case, in this example, I am traversing through this array, half of the length of the entire array, but still my complexity is going to be order of n because I will drop the constant. So I hope it is clear, and that's the interesting thing. So if you see here, we are determining the complexity of a given algorithm. So we are trying to understand how our code is running, executing, and this gives us an opportunity to optimize the code if needed. So if we are optimizing, then maybe we are reducing its runtime, the time or amount of time it is going to take when it will run, right? So that's it. I think explanation here is the same. We have taken 2 examples here, 1 2 3 4 5 and 1 2 3 4 5 6. And when we are taking these 2 examples, we are determining how many times our for loop is running. Okay, so overall eventually what we found is its complexity is order of n. So that's it for today, order of n. And keep learning, keep solving different problems, and ultimately you will build a solid background in big O world. With that, thank you and happy learning.